Hello and welcome. In this tutorial, we're going to implement the Belousov-Zhabotinsky reaction in Max. So I first came across the Belousov-Zhabotinsky reaction in a video by Patt Vira, who does really great creative coding tutorials in P5.js. So I'll put the link to their video in the description. And everything I'm doing in this video is essentially just a shameless ripoff of their video. So with this reaction, we're essentially simulating the interaction of three different chemicals. We will call them A, B, and C. And then some kind of diffusion is going on between them. I will base this on this tutorial or this article by Alistair Turner. So here the reaction is explained, and then on the bottom we have the processing source code. So this video is essentially me porting this code to jit.gl.pix.codebox in Max. I will also put the link to this article into the video description. So this tutorial consists of three parts. The first one is building a feedback system, because we're going to work with texture feedback. In the second part, we're going to implement the actual code within the feedback system. And in the third part, we're going to look at working with color, looking into how we can make this look pretty. So I'll start with an almost empty Max patch. Here I have a jit.world object as our OpenGL rendering context. Here is a jit.p window, so we can see what we're doing. And I also have an input video here. So starting with the first part, setting up the feedback system. First, we'll need a jit.gl.pix.codebox. Then as an input, I need a texture. Let's make this full HD. One here, and I'll need another one here. And then the output is going into the jit.world. And this time I'm doing the feedback system a bit differently. So the output is coming in the second input. And the first input is essentially just activating or advancing the reaction. So with this jit bang object, this sends a bang out on every frame to our texture, and then the texture advances the reaction inside of the code box. But the magic is just happening between the second input and the output. So what do I mean by that? First we need a, okay, now it is gone, something happened. I will just say dummy inlet is in 1. And then the state of the reaction, let's call this one state, is input 2. And output is then, let's say the result is 0 for now. And the output here is then the result. Then I can connect this here, or we can, just to illustrate this, I can say result is the state here. And what I now want to do is I want the reaction to take place essentially between the output and the second input. And every time I want to start a new reaction, I want to bang what's coming out of this video to then start the new reaction on a new frame of this video. So to do this, I will say through 0 for this texture, because what this does is, let's start this up. Now you can see the video that's coming through, but if I put the texture here in between, it doesn't come through anymore. It only comes through when this texture gets banged, and that's exactly what we want here, because every time I'm banging this texture, the reaction starts over again with a new input picture. So moving on to the second part, now that we have the feedback system set up, I will just clean this a bit so we have more space. So what do we need? First, we need for each pixel every neighbor, because for each pixel we're looking at the pixel itself and all of its neighbors and get the average value to then advance the reaction. So to get each neighbor, let's start with left. No, oh, I didn't mean to do that. So first we need the size of one pixel, so we can then look at the neighbor one pixel above, one pixel below, one pixel to the left, to the right, and also diagonally, upper left, upper right, down left, down right. So to get the size of one pixel, I can just say pixel equals 1 divided by the dimension of the whole texture. And then to look at the left pixel, I can say I'm sampling the input at the normalized coordinates, and then I'm introducing an offset of exactly 1 pixel. So this would be norm plus 1 pixel times an offset vector, and to the left it would be -1 on the x-axis and 0 on the y-axis. I will also say that we have a bound mode here. Let's use bound mode clamp. No, let's use bound mode mirror. So when we're at the last pixel on the left, for example, we don't want it to wrap around, but we want the texture to mirror. So no, I think this one belongs here. No, now it should be working. But I will need some more space so we can see what is happening. Okay, was this an old error or a new one? Okay, this seems to be an old one, so this seems to be working. And now I don't only need the left neighbor, but I need all the other neighbors. So I can copy this and say, okay, the right neighbor is essentially the same thing, but in the other direction. Yeah, let's copy this again. The neighbor on top would be 0 on the x-axis and 1 on the y-axis. The neighbor down is same thing in the opposite direction. And then we also need left up. Which is to the left, so -1 on the x-axis and 1 on the y-axis. Then I can use the same thing to do right up, which then is 1, 1. And then I can say left down. This is -1, and right down. This is 1, -1. So no errors. This is looking good. So we have 1, 2, 3, 4, 5, 6, 7, 8 neighbors. And now I want to get the average of the current pixel plus all the neighbors. So let's call this one average. And first we're considering the pixel itself plus left, right, up, down, left up, right up, left down, and right down. I will do something like this so it's easier to see what's happening. 1, 2, 3, 4, 5, 6, 7, 8, and the one itself that's coming in. And then we're dividing this by 9 because we're looking at 9 pixels essentially. And now we have the average of the square surrounding the current pixel. So now we can derive the chemicals ABC from this average that we have, but I will quickly push this up here and make a little bit more space down here so we can see the whole code at once. Okay, so A would then be the green channel of our average. B, oh no, the red channel, sorry, R stands for red. B is then the green channel and C is then the blue channel. So what we've done so far was a lot of work, but kind of boring, not very spectacular. So what do we have here? We're looking at all of the neighbors, getting the average, and then deriving the individual channels. And now we can do the step that actually counts, which is when we're looking at our article here. Yeah, which is essentially this. So we want to implement this into our code. So this means A of t, so t is the time. So A of t would be the current iteration, and A of t plus 1 is then the next step in time. So this means the next step in time for A is A plus A times alpha of B and gamma of C. So what is alpha, beta, and gamma in this case? These are, just factors by which we can scale the whole thing. So I will copy this, put it here as a comment. Is this the right thing? No, it doesn't look right. Okay, we'll just have to look at this one. Okay, we need alpha, beta, and gamma. And I will set them as parameters. Oh, and I just saw I made a mistake here. So this average should take input 2 and not input 1. And then I can get rid of them up here and we have some more space. So the first parameter, alpha, let's set this initially to 1. Then we have beta also 1, gamma also 1. And now we can implement this one here. So maybe let's just call it next A equals, what is it, A plus A times alpha times B minus gamma times C. So alpha times B minus gamma times C. So I will copy this, next B, next C. So looking at this one, next B is B plus B. And then inside here we have beta times C and alpha times A. So this should be a C. Here we have alpha times A. And here for the next C, we have C plus C times gamma A, beta B, okay. Is this correct? Yes. So these parameters aren't doing much at the moment because they're set to 1. But when we're changing them, we can also change how the reaction looks. What we also need here is to clamp this, because now it can go above 1 or below 1, but I want to clamp this between, oh no, I mean above 1 and below 0, but I want to clamp this between 1 and 0. So I will put this in parentheses and say clamp, then this whole thing between 0 and 1. Again here, clamp between 0 and 1. So this means if one of these values goes below 0 or above 1, it will stay at 0 or 1. Clamp 0 and 1. And now for the output, we're creating a new vector. And setting the red channel to the next iteration of A, the green channel next iteration of B, and the blue channel to the next iteration of C. So, did I get any errors? Yes, variable state is not defined. Is this still relevant? No. So let's see if this works. So I'm banging this and nothing is happening. Okay, why is this not working? I'm going to copy this. So here, the video is coming through. Here, the feedback is coming through. Ah, I see what I did wrong. I used again here inlet 1 when I wanted to use inlet 2. What about now? Ah, now you can see. This is some good chemical reaction going on here. And then we can expose these parameters to outside of the code box. Where is the gamma? And change some values around. Yeah, it looks very nice. And what we also can do is introduce a new variable, call this one scale, set it to 1 for now, to control the scale of the whole thing. So if I say that the pixel size is affected by the scale, I can then expose this to the outside, and if I'm reducing the scale, you can see that this becomes finer. So the swirls are a lot smaller now. Okay, this is it for the second part. We've successfully implemented the code. But yeah, now we want to look more into the color side of things, because as you can see now, A, B, and C just represent the red, green, and blue channel. But we could also do something like, okay, just looking at the red channel and controlling the color output with just the information of the red channel. So to do this, I will create a jit.gl.pix and call this one color. And before going into our output, we're going through this one here. And here, yeah, when changing the color, be sure to not do it inside of the feedback loop, because then this reaction won't work anymore, because everything that's happening inside the feedback loop will then also influence how the reaction is behaving. So we're doing this just as a last step before we're going into the output. So what we could do here, for example, we could just take the red channel, so Swiss R. I will make this a bit bigger, which is also kind of cool to have it in black and white. But we can then use the red channel to control color information. So we can use HSL to RGB. So this, as the name suggests, turns HSL, so hue, saturation, and light, into RGB values. So we could create a new vector and say, okay, 0.5, 0.5, 0.5. This means that the brightness is 0.5 and the saturation is 0.5, and then the color, the hue itself, will be controlled by the red channel that's coming in. We could also scale this and say, okay, just take 0.5 to 0.25 to 0.75 to get different colors, or to 1 or 0.5 to 1 or something like that. Or we could take the whole RGB that's coming in here and just interpret it as HSL, which also looks kind of cool. Yeah, so depending on what you're going for, you can change the color that's coming in here. And yeah, playing with these values, of course, gives you different results. No, I like this to be rather small. To 1.1, I don't know, 0.9. Oh, this also looks very nice. Yeah, so this is essentially what I wanted to show you. I hope you found this useful, and thanks for watching.